Okay, so today we're going to start chapter 2. And chapter 2 is going to start off with a lot of review. Mostly because I thought you needed to know a lot of this before we really even got started with class, and so I talked about it earlier. But we should go over it again and just make sure it's cemented in there before we start talking about the more complicated aspects of chapter 2. So we're going to go through and we're going to remind you about ionic and covalent bonding so that you remember exactly what that is and what the differences are, because it becomes really important here. All your naming is still really important here, and knowing how to identify between each one is very important. Now we're going to introduce Lewis dot symbols in a little bit more of a formal nature. Before we kind of threw them at you and said, this is some really simple ones, this is how we represent them. Now we're going to go through and we're going to do a bunch of very complicated ones that go way more into depth on what exactly is going on, which will lead us into trying to talk about how molecules look like and doing geometries and things like that. Then we're going to do some more Lewis dot structures that are even more complicated. And more Lewis dot structures. Really, chapter 2 is kind of all about Lewis dot structures and getting good at them. Once we've really got that down packed, we're going to go through and do some bond strength and length comparisons so that we can see how they're related to each other. So, again, some review from last time. So bonding is all about trying to figure out how to complete octets or make things more stable than they were. Now you can do that by, in something like this case, sharing electrons. If two different electrons have 6 valence electrons, they can go share them. They can take 2 of their electrons, share them with each other, and then form some bonds there so that they each can have 8. There's our 3 main types of bonding. We have our ionic bonding, our covalent bonding, and our metallic bonding. Remember, these are important for knowing how to name them because we use different names for our ionic than we do covalent. And they're very different from each other. So in ionic, you're trading an electron. Sodium says, hey, I have an extra electron. And chlorine says, well, I don't have enough. And so the sodium gives its electrons to chlorine. Sodium becomes a 1+. Chloride it becomes a 1-. They share the electrons, or they switch the electrons. Now, that plus and minus, well, now they're attracted to each other. They're like little magnets, right? So they're going to be attracted to each other, and that's how that bond forms. Now, something that's covalent, on the other hand, they're going to share the electrons. So something like carbon monoxide. Carbon and oxygen, both of them don't have quite enough electrons. So if they share some of them, now they can each have what they need. And so they're kind of stuck together by the fact that they're sharing the electrons. Now, we need to know how to differentiate between the two, right? So the way that you decide whether something's ionic or whether something's covalent is, for right now, seeing where they are in the periodic table. So if something's on the right-hand side and the left-hand side are 2 different things, like sodium and chloride, you have a metal and a non-metal, that means that you're going to have an ionic bond. Something that's covalent will be 2 nonmetals, so everything up in that top right-hand corner of the periodic table. If it's made up of things over there, that's going to be covalent. Now, this is a little bit of an oversimplification, and toward the end of the chapter, we will start talking about how this isn't quite exactly how things are, and that really there's a gradient. Some things are more ionic than others. You could have a purely covalent compound, and then there's sort of a gradient all the way up until the ionic ones. And so we'll talk about that later. And then we had the metallic, which we aren't talking a lot about now. You'll get into that more in Chem 1B, but we did want to talk about it a little bit. And the main difference here is that all of your electrons are delocalized. It means that one particular electron doesn't really belong to any particular atom. And so there's this kind of sheet of atoms and sheet of electrons all bonded together, which means that you can pass electrons through it. If you put an electron in one side, you can make it come out the other. And so that's why they're conductive. Now, this is sort of new. We didn't quite get into this before. And there's a little bit of background here that you sort of need to make sure you know from the fundamentals that maybe you glazed over a bit. So all of the processes that consume energy are called endothermic. So think back to your high school or 1P experiences and think about these words coming back to you again, right? For taking in energy, that's endothermic, bringing in energy. If you're releasing energy, you're throwing energy out, that's exothermic, right? Think exoskeleton on the outside. It's putting energy out into the environment. We're going to go really far into that in Chem 1B. Here we just need to be able to remember what's endothermic, what's exothermic, and the signs that are related to those. So we want to talk about the energy of an ionic bond. So think about, before I show you the next slide, which has a lot on it, what I said before about how we form an ionic bond. An electron goes away from one atom, it goes to the other atom, and then the plus and the minus are attracted to each other. So we have three kind of steps there. We have an ionization energy, the ion being, or the electron being pulled off an atom. We have an electron affinity, an electron coming into an atom, the other one. And then we have this other energy that comes from the attraction of a plus and a minus. And we have that energy. So three energies. And for it to be favored, we want it to be exothermic. We want it to give off energy. If we have to put a bunch of energy in to form something, that's not going to be favorable. So this is sort of the background for the next slide. Okay, so this is what I just said, all kind of laid out formally. First, this one. We have sodium losing an electron. We have an electron going away from the sodium. Now we have a word for that, right? We talked about it just last lecture. We called that ionization energy. An electron is leaving. So the only real difference here is, instead of talking about a trend, I just put a number on it. And I put a plus number on it. So it takes energy to be able to lose an electron. So this endothermic reaction in quotes. Now Cl is going to gain an electron. It's going to take an electron in. So that's, in other words, an electron affinity, right? Once again, what we talked about last time. And again, we'll just kind of give it a number now. So that takes a little bit of energy. And so that becomes 340, or negative 349. So these are just numbers for these specific things. Obviously not something that you would ever be expected to memorize. What I really want you to get out of this is the magnitudes. So 1B will go into more how to calculate energies and how to deal with them on a very mathematical form. I want you to kind of think about the magnitudes here. So we have a plus energy, we have a minus energy, so we have an endothermic, we have an exothermic, taking in energy, giving off energy. Okay, so once we do that, now we've switched to the electrons, right? We've taken away the electron from one and we've put it on the other. One took in energy, one released energy. Now we have sodium chloride, or we have sodium plus and chloride minus attracting each other. And that's favorable too. That's exothermic as well. So we get a negative 787. So you may want to add some little notes here, you know, if you've forgotten what designates an endothermic and an exothermic for signs. Pluses are endothermic, minuses are exothermic. So in order for this to be energetically favorable, you want it to be exothermic, which means, do you want a positive or a minus? Remember, endothermic, exothermic.